A very good day I bid to Doctor and also everyone. Our group has chose Niels Bohr as the title of our assignment. Our team consists of 6 people, which are Michelesta, Nunku Farisha, Nur Shahira Nadira, Jill Justin, Nur Farah Najwa, and Alia Natasha. Introduction. Niels Bohr was a famous physicist who made major contributions to quantum theory in the early 20th century. Born in Copenhagen, Denmark, in 1885, he studied physics and later worked with J.J. Thomson and Ernest Rutherford in England. In 1913, Bohr introduced the Bohr atomic model by combining Rutherford's atomic theory with Planck's energy quantization concept. His model explained electron energy levels and atomic spectra, becoming an important foundation for modern quantum mechanics and influencing the fields of physics and chemistry.
Niels Bohr proposed that electrons revolve around the nucleus in its quantized orbit. He introduced the idea angular momentum, which is expected to reduce an atom emit or absorb energy only when electrons jump between these orbits. The first possibility, the electrons is in fixed orbit. Electrons orbit the nucleus in fixed orbit, which is stable orbit, correspond to the discrete energy level. Electrons will lose energy unless they jump to a different orbit. Energy emission or absorption, which is energy in exchange only when electrons jump between levels. Absorption is electrons move to a high orbit, while emission is electrons fall to a lower orbit, releasing photons. About the spectral lines of emission, which is the frequency of radiation corresponds to the energy difference between two orbits. Model only work well for hydrogen, but it fails for atoms with more than one electron. It could not accurately predict the spectra of helium, lithium, or other massive electron systems. The model could not extend the splitting of spectral lines of cells under magnetic or electric field, known as the ZMAP stack and substack, that require more advanced quantum theory. In chemical properties, the Bohr model gave no insight into chemical bonding or periodic table. It could not explain why atoms form molecules or how their properties vary across the periodic table. Lastly, in classical quantum synthesis, Bohr's model with classical mechanics with arbitrary quantum rules. The Bohr model of atoms introduced in 1913 revolutionized atomic theory by which it took electrons and energy to discrete values. It proposed that electrons orbit the nucleus in stable energy levels without radiating energy with its orbit level by an integer known as the quantum number of n. Transition occur when electrons move between these levels, absorbing energy to jump to high orbit and releasing the energy as a photon of light when returning to a lower orbit. As expressed by the relation E equal to hv where h is time constant. He further introduced the concept of angular momentum quantization given by mgr equal to n multiplied by h over 2 pi, which successfully explains the observed hydrogen spectra. The complementarity principle introduced by Niels Bohr emphasized that particles can be of just light and particle-like properties depending on the experimental concept. Closely linked to the Heisenberg principle, it highlights the fundamental limits of measurement, showing that position and momentum cannot be determined simultaneously with absolute precision. This principle provided the foundation for quantum chemistry, explained the stability of atoms and their behavior as specific reference to Bohr's atomic model.
Let's figure out how Bohr finding influenced their era. All of the scientists struggled to explain why atom was stable and how they produced distinct spectral lines. So Bohr introduced the idea that electrons move in fixed energy levels around the nucleus, so that they can only gain or lose energy by jumping between these levels. His model successfully explained that hydrogen emission spectrum, providing strong evidence that energy is quantized. This breakthrough supported the emerging field of quantum theory and helped bridge the gap between classical physics and modern quantum mechanics. Bohr finding influenced many physicists of his time, inspiring further research into atomic structure and quantum behavior. His work laid the foundation for later contribution by scientists such as Ernst Schrödinger, Werner Heisenberg, and Wolfgang Paulin. Bohr became one of the key figures in the development of modern physics and quantum chemistry during the early 1900s.
Before Niels Bohr introduced his atomic model, scientists were still trying to understand the structure of the atom. In 1897, J.J. Thomson discovered the electron and proposed the Planck pudding model, where electrons were embedded within a positively charged sphere. Later, in 1811, Ernest Rutherford's foil experiment revealed that atoms contain a small, dense, positively charged nucleus. This led to the Rutherford atomic model. However, Rutherford's model had a major problem. According to classical physics, orbiting electrons should continuously lose energy and eventually collapse into the nucleus. Scientists also could not explain why atoms produce specific line spectra when heated. This limitation showed that a new atomic theory was known. Both atomic model marked an important turning point in the development of quantum physics. This theory demonstrated that energy with the atom is quantized, meaning it can only exist in specific amounts rather than continuously. Although the Bohr model was later improved by modern quantum mechanics, it provided the foundation for understanding atomic structure and electron behavior.
Ever wonder how Niels Bohr's 1913 atomic model is still making waves today? It's completely driving advanced computational chemistry, because Bohr proved energy states are discrete to the scientists can track energy at the ultra-fast femtosecond scale using 2D electronic spectroscopy. We are now mapping out molecular qubits using quantum computing for quantum chemistry, or better known as QCQC. By natively simulating quantum atom interaction, researchers are vastly accelerating complex molecular modeling and modern drug discovery. To see this in action, take a look at these incredibly detailed spectroscopy graphs and the molecular matrix diagram. The graphs show electromagnetic wave amplitudes being tracked at trillions of seconds, while the molecular grid illustrates a triplet ground state carbon embedded in a crystalline matrix. Bohr's foundational rules inspired modern pioneers like Dr. J.D. Saltz and his team to map out this exact coherent energy transport. It's essentially Bohr's quantum leap captured in real time, allowing us to physically see excited delocalization. Zooming into the nanoscale, we have artificial atoms, or famously known as quantum dots. Now check out these glowing bars. They all contain the exact same material, but they emit different rainbow colors, strictly based on crystal size, which actively detected by Bohr's quantization rules. A tiny dot glows blue, while a larger one glows red. Here is a fun tip. Dr. Monkey Bandy recently won the 2022 Nobel Prize in Chemistry for perfecting these quantum dots. Today, this direct application of discrete energy is completely revolutionizing modern bioimaging, as you can see in the detailed medical scans on this slide. Finally, we drop the temperature for high energy physics and complex magnetism These 3D lattice of red and blue atoms represent geometrically versatile materials such as terbium oxychloride. By applying Bohr's quantization of angular momentum, physicists can record incommensurate spin density waves and complex high hysteresis behavior at extreme cold, specifically near absolute zero, below 2.0 Kelvin. Both saturate all theories are literally unlocking the coldest, most complex magnetic mysteries of our universe.
We can summarize that Bohr's idea have contributed to quantum chemistry field by inventing Bohr atomic model, which is explained that the electron have a fixed quantized energy level by traveling in a fixed and specific orbits. The findings transformed their era by successfully explaining the atomic spectrum, which researchers had previously found difficult to explain. His legacy continues to impact modern science and technology by contributing in some fields, such as advanced quantum computing, nanotechnology, and more.
That is all from us. Thank you.